Morning, everyone. I'm Simran Cortez. Currently, I'm a postdoctoral fellow at the University of Alberta in Edmonton, Canada. First of all, before I begin, I would like to thank all the members who have been kind enough to give me this opportunity. To begin with, today I'll briefly outline or introduce you to soil microbial technology, which serves as a self-powered system capable of generating green energy as well as treating contaminated soils. Begin with a brief introduction about soil microbial fuel cells. Soil microbial fuel cells have evolved as a new method of renewable green energy generation. They hold the potential as sustainable, carbon neutral technologies that are capable of soil biodiversity. Soil microbial fuel cells consist of a soil bed with two electrodes one electrode embedded in the soil, which serves as a node, and the other electrode kept or maintained at the soil-air interface, which serves as the cathode. Now, for the electrochemical reactions or the electrochemical circuit to complete, these electrodes are interconnected through a connecting wire, which is further connected across an external resistor to close the circuit. Now, as the electrochemical reactions take place, the electrode potential across the system deviates. And as this electrode potential develops, as the gradient develops, the output is the voltage that we convert or further calculate in terms of power. So a typical soil microbial fuel cell consists of an electrode assembly consisting of an anode and a cathode. Anode embedded in the soil, while the cathode maintained at the soil-air interface. The feed for such systems could be any kind of soil compositions. There are extensive researches where instead of soil, wastewater from different natures, from different kind of inputs or sources has been used as a fuel, being rich in organic matter. All we need for this technology to act or to work is a substrate that is rich in organic matter. And as we know, soil itself inherits a large organic content, and along with that, it also has a wide range of microorganisms. Now, these microorganisms are capable of degrading the organics in soil, and as these organics are degraded, the electrons or the energy released in terms of electrons and protons is used to harvest energy from the soil as feed. With the passage of time, the microbes in the soil will degrade the organics, and as a result, a biofilm will develop across the anode. Now, as this biofilm develops and electrons are transmitted to the external circuit to the cathode, the protons are transferred from across the soil bed to the cathode. And as this transmission occurs, a potential gradient develops. But the growth in this potential gradient is not instantaneous. It takes time for the biofilm formation and further for the system to stabilize and reach a good stable potential. Now, as the potential develops, we observe a steady increase in the cell SMFC's voltage recorded, with simultaneous positive increase in the cathode potential, while the anode potential shifts towards the negative end. For this for this work, my special focus was on developing electrodes, particularly anodes, that would facilitate the enrichment process and that allow us to develop a system that is well inbuilt with capabilities to have stable power generation over a longer period of time and also offers compatible conditions for the biofilm and the microorganisms. For this, we use the conventional graphite felt that has been extensively explored, owing to its conductive, porous, large surface area. But the challenge is to ensure that the biofilm adheres to the surface. Uh, as for those who have worked with graphite felt, must be aware that graphite felt is highly hydrophobic in nature, which prevents the biofilm formation during the early stages of the operation, or it slows down the biofilm deposition on the electrode surface. So to facilitate this process, I came up with a strategy to decorate the surface of the electrode with compositions that would be that are metal oxides. I used cobalt oxide nanoflowers decorated on the graphite part using a hydrothermal process, which was quite pretty simple. However, after carbonization, when we use these electrodes in the soil, we observe that over a period of time, the metal deposits on the graphite felt detached from the surface. Basically, there was leaching of cobalt in the soil. So to prevent them, another strategy that we adopted was to encapsulate this composition of graphite of cobalt oxide decorated graphite felts with polyethylene, which itself has high conductivity, highly biocompatible for the microorganisms, and could also slow down or even limit the leaching of cobalt in the soil. So we developed four different systems where we use the plain graphite felts as the cathode, and corresponding to them, four different anodes were developed and used. This is a schematics of a typical SMST system where three electrode replicates were developed to have a good combination of data and to eliminate any random errors during the operation. So when we did the scanning electron microscopy, we clearly see that the deposition of the metal oxides on the surface generates highly uneven roughness on the surface, which is likely to facilitate the biofilm formation and the microbial adhesion on the electrode surface. However, these nanoflowers or the nanostructures being metal drawn, they offer one limitation, and that is smooth surface. Thus, to overcome that limitation, we encapsulated the surface, the electrodes with polyethylene and observed highly porous rough morphology on the graphite fibers. Then we further analyzed the contact angle analysis to confirm if there is an advantage or if there is a benefit of these different modifications on the hydrophilicity of the electrodes, and we clearly observed that the contact angle of a water droplet on a graphite felt electrode decreased from nearly 139 degrees to 115 degrees, which may not be significant in terms of magnitude, but qualitatively, it was good enough to lead to a big difference in terms of the enrichment as SMC enrichment. Further, we confirmed the electrochemical performance of the different electrode systems at the different stages of the operation, and we observed that encapsulation of the cobalt oxide decorated graphite felt with polyethylene resulted in an enormous increase in the electrochemical surface area, which of course is beneficial to ensure that the electrodes that we have developed are capable of energy storage and also can allow long-term operation rather than the unconventional graphite wells. In terms of power generation, a high power generation was observed with the hybrid composite of polyethylene encapsulated cobalt oxide graphite felt. The performance of the systems with cobalt graphite felts was the performance of the optimal catalyst was nearly 63% higher than the cobalt oxide decorated graphite belts and over 16% higher than polyimide graphite belts. However, in comparison, however, in comparison with the conventional electrodes, we observed that encapsulating electrode, however, we comparison with the electrodes, we observed that encapsulating the electrode with polyimide not only favored microbial adhesion, it also favored the long-term operations and a higher power efficiency of the systems. Other than power generation, as I already said, these systems can also be used for soil decontamination. Currently, it has been stated that 50% of the world's soil is degraded, and the energy production agricultural activities are being the major reason for 80% of soil pollution. Further, persistent organic pollutants can increase the harmful potential by up to 70,000 times because they remain in the atmosphere for several years before they degrade. This pollution is, as we have observed, is interfering with the food chain. Half of the global population is drinking water contaminated by the environmental pollutants of land. So this calls for this raises an alarming demand for a technology that could facilitate the degradation process or the remediation process of contaminated soils. Here, soil microbial fuel cells could be a good option. Not only being low-cost alternatives, they are easy to operate, compatible for remote operations, and offer a possibility of autonomous operations with generation of useful power, as I already showed you in the previous result. Now, for decontamination, with the objective of decontamination, we realized from the preliminary studies that the main stage or the most important crucial factor was to increase the interaction area between the contaminated soils and the electrodes, that is the anode. So we came up with a multi-anode corresponding to a fixed cathode strategy. A fork-like configuration of anodes was used, and it was tested in different soil combinations. Briefly, 3 different strategies were adopted. One was natural attenuation, where the systems were saturated with milky water. Second was biosimulation. Third was a combination of biosimulation and bioaugmentation. For each combination, 3 different soil compositions were used. S signifying pure, contaminated or polluted soil that we received from our partners under the project Greener. SV represents the contaminated soil diluted with 2 weight by weight percent vermicompost, and SVC is a combination of contaminated soil with garden campus soil in a ratio of 70:30 and 2 weight by weight percent of vermicompost. Before we move ahead, briefly, I would like to outline what basically biostimulation and bioaugmentation are. So biostimulation and bioaugmentations are one of the most popular bioremediation strategies that have been explored extensively owing to their high efficiency in terms of the contaminant degradation. So this work was done in collaboration with University of Burgos and University UAM. Biostimulation basically refers to enriching the soil with suitable nutrients that would facilitate the growth and development of microorganisms that are capable of degrading contaminants. Now, the second stage operation strategy was bioaugmentation. Bioaugmentation is an additional step in other than the nutrient solution, where an bacterial inoculum is developed by isolating it from hydrocarbon contaminated soil. It is then grown up. It is then followed by growing up of the microprecontortia and then mixing it into nutrient solution and soil for the further amendments. This is briefly how this microbial fuel cell setups were established in the lab. As I said earlier, three fork like anode configurations were used against one cathode liquefied fed cathode. Now, due to treatments, we observed that in soil microbial, and as I said, in soil microbial fuel cells, microorganisms transfer electron from the organic matter to the electrode, creating an electric current. Now, this electron transfer influences the redox potential of the surrounding environment. Some microbes that are involved in this process are capable of secreting protons, and these protons can influence the pH of the local environment, making it more acidic, as observed during the first 15 days in most of the cases. With this acidification can be associated with introduction of inorganic and organic nutrients through the nutrient solution used for biostimulation and vermicompost treatments, which could be related to increased CO2 production due to organic matter mineralization. On the other hand, some microbes can consume the protons, leading to more alkaline environment. So this interplay of electrons and proton exchange during the SMFCs affects the soil pH. If we look at the bar charts given, we can clearly see that contaminated soil is acidic, which is not favorable for bioremediation or for the survival of microorganisms. However, by day 16, neutral pH was recorded for all systems under bioremediation, which suggests that addition of external microorganisms or nutrient solutions to stimulate the growth of soil microbes and adjust the microbial community not only facilitates the ideal environment for the degradation, but also accelerates the microbial metabolism, which can be speculated, from which it can be speculated that SMFCs and the biostimulation and biofermentation may be capable of highly better degradation of pollutants in soils than those under natural attenuation. Further, we analyze the effect of organic matter on the soil microbial fuel cell output. Now, organic matter plays an important role when we are discussing about the performance of soil microbial fuel cells, because the entire gist of the system depends on how efficiently the microbes can degrade these organics, leading to release of electrons and protons in the system. Now, hydrocarbon degrading bacteria often require additional soil carbon sources to facilitate the breakdown of hydrocarbons. The presence of organic matter can stimulate the growth and activity of these bacteria, which leads to increase in the hydrocarbon degradation rate. Now here, we observe that clearly with the dilution of contaminated soil with vermicompost and campus soil, there was an increase in the organic matter. The vermicompost and soil served as a nutrient solution rich in organic matter, which leads to increase in the microbial activity. This in turn stimulates the existing organic matter in the soil and results in an overall increase in the soil organic content. However, with the addition of the nutrient solution under biostimulation, it may be possible that if the solution is rich in mineral nutrients, that is, then it may not have a direct effect on the soil organic content. It's as observed here. For biostimulation, the solution that we used, the PHP solution that is rich in mineral salts, which is necessary or which helps to facilitate the growth of microbes, but it did not show any significant effect on the organic matter. Electrochemical performance was investigated, and it was observed that the cell potential or the voltage potential or the voltage generation in the soil microbial fuel cells with soil diluted with vermicompost and campus soil was highest compared to the soils with vermicompost. Accordingly, the power generation for systems with SVP under biostimulation was highest, followed by those with natural attenuation. However, for other systems that were systems with contaminated soil or systems with 2% of vermicompost under biostimulation, under bioaugmentation, or any other strategy, power generation was merely any magnitude. Seepage degradation was observed, and we observed that the TPH, that the degradation rate with biostimulation and bioaugmentation were far better. The TPH degradation rate with a combination of biostimulation and bioaugmentation was far better than than natural attenuation or just biostimulation. Although the degradation rates were lower than the controls by nearly 20%. Now, the controls here were basically the SMFC, the soil combinations without any SMFC. So, further, we also state that the efficiency of the degradation was with soil dilution. So, the takeaway messages would be that the voltage generation by SMFCs operated in pure soil contaminated SMFCs was very pure. The dilution of soil was beneficial for the SMFC operation. In soils, SMFC performance did not improve with biostimulation or bioaugmentation. The TPH degradation is enhanced with the integration of biostimulation and bioaugmentation, but the oxidated products can improve. The oxidation process can be improved by applying an external potential. Thank you.